So all these give you motivation. We want to solve, or we want to know how to solve this kind of differential equation. So in last semester, we learned a lot about how to solve the Poisson equation. It's just the Laplacian operator on the field, and then we have the solution. We know the because this we get to this solution because we know the green function for Laplacian. Laplacian is just one over the free space green function is just one over x minus x prime, and that's simple enough for free space. And with boundary, then obviously you get very complicated, and you spend a lot of time, different geometry to solve for the green function. But at least for the D'Alembert operator, we stay with free space at first and find the green function. It will take a little bit of work, but then the final form is not too bad, right? So we'll do that. All right. So we want to find the green function. Ultimately, we want to find the green function of the D'Alembert operators. Is the Laplacian of G. That should depend on x prime, t, d prime, right? And then minus over the c squared, also squared, also t squared, g, the same g. The right hand side should be our delta function. We want to do that. We want to solve for g, and that how you set up the equation for the green function. That's what we do, and we'll do it following Jackson. I mean, there's not the only way, and probably can solve it wider way instead of what Jackson did. Jackson do it in 2 steps. So first, solve for the when you solve, do it Fourier transform, which some of you, I mean, haven't taken math physics, so I don't know how familiar with Fourier transform, and supposedly even undergraduate you heard about Fourier transform. So, but we'll apply it anyway. Once you do a Fourier transform, basically get rid of t, and then you solve for the green function for that equation first. That is called the Helmholtz equation. Right. The idea is a g in here. So this is, it depends on both x and x prime and t prime, but you simplify the notations. Just keep x and t, and or the x prime and t prime you treat it just like parameter first. In fact, I actually should follow Jackson more closely. In fact, it's try to solve a green function for a scalar first. So we try to. In fact, it's not even a scale. We're trying to find psi, capital psi, the same with a general function f x. All right. And to solve that, we do a Fourier transform. This obviously depends on x and t. And we're doing Fourier transform in time, keeping spatial dependence. And that would be, I think, using for Jackson's notation. He put the 1/2 part in what we call the inverse transform. phi omega t, or x omega is minus u d omega minus infinity. Okay, is it familiar? Is it? Is it okay for Fourier transform? It's just the only thing that is Jackson using this convention that you use the same symbol for the function and the Fourier transform, which sometimes is confusing. But you just need to be careful. And I usually would put another label on that, like a tilde or whatever you try to indicate this is a Fourier transform. But Jackson used the same symbol. But, anyway, just need to be a little careful. And the Fourier transform, you have no 1/2 pi, you put all the 2 pi. Some people like to put the square root of 2 pi in both inverse and forward Fourier transform that make it symmetric. But again, for Jackson, this is fine. Xt infinity. Okay, so that is Fourier transform, and then you basically do a Fourier transform, find out the equation for the Fourier transform. You can either do this operator on both every term, or you treat it like this one is substitute this into here, and the second time derivative will pull out the only operate on this exponential function will pull out minus I square, which is -1. Okay, so that will pull omega minus omega square, and then becomes a plus omega square for c square, and then every term has this integration, and then divided by 2 pi. So and then you take out just the integram, and that the integram will satisfy this equation. Laplace x omega has become plus omega square of c square. So, and the right hand side would be the Fourier transform. Okay, and the finest simplification is define a variable k. So k is omega over c, or you can say the square k square omega square over c square. So change that to k square. Okay, just a little simplification in writing. All right, so you want this for general differential equation of this form, you change in the Fourier transform becomes like this. Now the next step is to try to find the green function for this one. So green function now is just forget about omega, just in the same omega. So now this g should depends on x prime. Actually depends on k also, but the Jackson just label it a subscript k. And then use the right hand side as delta x. And solve for this green function. This is the green function of the Helmholtz equation. So the right hand, if the right hand side is 0, then this is the homogeneous Helmholtz equation. With non-zero right hand side is inhomogeneous Helmholtz equation. Right, and now we try to solve that by making certain argument, and we consider free space and by the symmetry, just like what when we solve the green function for the Laplace equation or the Poisson equation, then we know that this is the green function should only depends on the magnitude of this vector. What we define this as what vector capital R. and the G becomes G as a function, G sub k. It's a function of R only. R is the magnitude of this R. Capital R to capital R is just x minus. Okay, so that's take into effect that we have a homogeneous problem, and then we use the spherical coordinate using R vector as a coordinate system. So using R as a radial vector. So this becomes, the Laplacian becomes just the first term in the spherical coordinate of Laplace. The Laplacian, which you can look that up right away from Jackson's table using spherical coordinate, the Laplacian, just taking the radial term, R term, and then remember there's a note in Jackson that that's spatial part, the radial derivative part has two forms, and we are using the second form. So that make it 1 over R e squared. Treating other as parameter, this become a total derivative on G. It depends on R. Actually, R times, if you look at the R times, not just this one, R times. That's just from the table, Laplacian, using the radial, R as the radial curve. This term becomes this one, and then plus k squared, G squared, that equals to minus 4 pi. Delta function R. Right. And now we solve this in 2 steps. The first step is for R not equals to 0. And the radial coordinate not equal to 0, the radial vector is not 0. And then this vector green function is 0, right? And the right hand side is 0. And then this equation becomes, we write it in this form. Plus k squared multiply R to the this, because R is not 0. Right. So the form is like this. So from this form, can you write down the solution for R G is okay? Now this bracket is like a function. It's what is this? Simple harmonic oscillator. Right? Everyone can see that. So this equation is a simple harmonic oscillator for this function. The function with included in this bracket. So the R times G sub k. So R times G sub k is we can use sine or cosine or exponential function with I times argument. As it turns out, using the complex form is easier. So we'll write G sub k as divided by 1 over R. And then there will be 2 terms, A, B, R. And there's a k here, so k times B. The 2 arbitrary, for now it's arbitrary. So that's the general solution of G sub k. Right. And this for R is not 0. Right. Yeah, this is yeah, you can say that it's homogeneous because we said that it's 0. But we are solving the green function now, right? But we need to match it to the function, to the part that R tends to 0. Therefore, R tends to 0. we need to be a little careful now. Not totally set the right-hand side to 0 because we let r tends to 0. So this is a delta function is actually a limiting process. So when you take the limit of the arguments goes to 0, the delta function is large, right? I mean, when the argument goes to 0, the delta function becomes large, right? In that case, you compare the other terms, then the function, the term that in the Lambert equation with the k squared, that you can ignore this term with this term. So you can just say that the Laplacian, or you can say that you multiply by r in here, r here. So that you ignore this term, right? That is minus 4 pi. Actually, I should keep that. And remember, this is still the Laplacian. This is still a Laplacian of G. And so as R, for R very small, consider this R very small, then this becomes like the green function, the equation for the green function for the Poisson equation is there. And we know the solution. We know the solution for that, obviously. It's just 1 over x minus x pi. So the g sub k is just 1 over r in that case. Right? And so you have r not equal to 0 is this one, r goes to 0 is this one. So the two solutions must match. So to match that, you take the r tends to 0 limit. And when r tends to 0 for finite k, then the exponential function becomes 1. This is 1. This is also 1. This is a plus b. So this must equals to a plus b. Okay, and that implied a plus b equals to 1. Okay, so that is kind of important here. So there, at first we say that a and b are arbitrary constant, but now they actually satisfy equations. So they have some constraint. So instead of two arbitrary coefficients, we just have one. You either choose A or B as arbitrary, and the other is solved by this equation. If you have A, then the other is 1 minus A. Okay, so that was the green function for the Helmholtz equation. I don't know if I have time to finish this derivation.